Hey guys, we're going to go ahead and start on our next little section after we've talked about the image intensifying tube and its components in the previous video. We're going to pick up on the brightness that this image intensifier actually brings us, and that is called brightness gain. It's going to be starting on page 678 in chapter 38. Let me get my little PowerPoint friend here pulled up. Get it sharing. Okay, guys. So now we're going to discuss how much brighter the images actually are when the remnant beam has gone through the image intensifying tube. There's actually many ways of calculating this, but we know that the purpose of the image intensifier was to brighten up that very dim image. Remember, you're only having very few x-rays come out of the patient and hitting the input phosphor of the image intensifier, right? So we had to go through all those levels, all those different components to get that weak signal amped up by the time it got to that bottleneck of that accelerating anode with that $25,000 voltage on it. So it's pulling those electrons really fast, and there's ways of measuring how much brightness we've actually gained. We already know about one of them called minification, but we'll refresh on that. So brightness gain, minification is one part of it, and it's the concentration of electrons onto an output phosphor much smaller than the input phosphor. So that's simply telling us, and here's the calculations down here at the bottom, but minification simply tells us you're forcing something really large, pushing it, giving it a lot more energy, and then you're pushing it through a much smaller 1-inch output phosphor. Okay, that's the minification gain. You got they're so big, so many electrons, they're spread out right behind that output phosphor. Now that your light has interacted with the photocathode and released electrons, but they're spread out, and you'll see because of those electrostatic lenses, there's accelerating lenses, they're pushing them in. So they're getting more condensed, really tight. And that is where we're getting minification, the word minification from. The formula for the circular area is going to be what you calculate for each the input and output phosphor. And then you're going to take those two and set it up in a ratio, and then actually divide them up, and you'll get a factor. That's really your magnification, your minification gain, or your brightness gain. So if you have an input phosphor of 30 centimeters, you use the formula pi radius squared. So we know pi is always 3.14. Radius, if you remember from your geometry, your radius of a circle is actually half of the overall diameter. So half of 30 is 15. 15 squared times 3.14 gives you 706 squared centimeters. It's a lot of area. The area of your output is very small. It's 1 inch or 2.5 centimeters. They're both equal. So we got half of that to get the radius is 1.25. Squaring that, multiplying it then by 3.14, which is pi, you're going to get 4.9. So you're seeing the input is very large, 760 square inches or centimeters, versus 4.9, we'll round that up to 5. So we have 706 over 5. 706 divided into 5 gives you 141 times brightness. And that's just through minification. There's something else that we briefly talked about in the previous video. Brightness gain can also be influenced by what we call flux gain. And guys, I want you to look this up in your book on page 678. First, on the very top of the first column, it says the ratio of the number of light photons emitted by the output phosphor to the number of X-rays striking the input phosphor is called the flux gain. And obviously, these two items, the light photons being emitted and the X-rays coming in, those are being manipulated by that kinetic energy from those accelerating lenses. So it says the ratio of increase and kinetic energy from the acceleration of the electrons from the cathode end to the anode end is called flow gain. But I really think that it should be defined as page 678. This is really true, but it's telling you the mechanics behind it. So I would say that the ratio or flux gain or flow gain, as those electrons are flowing through, what is the output of the light photons coming out of the output phosphor against the number of X-rays going in? That is your flux gain. And it's really not something you'll calculate. They'll normally give you that. But you need to know that your minification gain and your times your flux gain will give you your total brightness gain. So they gave you a flux gain, just an example of 70. They give you a minification gain of 64. You multiply those, and now we have 4,480 times brighter. So your total brightness is 4,480 times brighter. And typically, the brightness ranges from 5,000 to 20,000. So your overall brightness gain is the product of minification, that is your input and output ratio, times your flux gain, which is the number of X-rays going in, number of light photons coming out, the ratio of that. And again, that's something you wouldn't be able to actually calculate because it's billions of them, but they'll normally give you the flux gain. But again, you won't be asked. You'll be asked by definition. And again, I want you to know the flux gain, flow gain. I want you to know the ratio that is stated on page 678 at the top of the page there in that very first paragraph, the carryover from 677. Okay, a multi-field tube and magnification modes. These two things go together. This is on page 678 in your book. Your field of view is actually the area of your input phosphor. How much of the anatomy are you seeing? If you have a large field of view, you're seeing more anatomy, and it requires you to do what they're saying. It says less panning. Panning is when you're taking the handles of your image intensifying tube, which is over your patient. Remember, the tube is underneath the table. You're panning and moving it to see the different parts of the chest, the abdomen. Now, if you need to zero in and zoom in on something, you will want to use a smaller field of view. So that's telling you you're using less of the input phosphor. The less input phosphor that you use, it ends up magnifying the image on the other end of the output phosphor. Okay, so magnification mode, it's actually, you're seeing less field of view, less anatomy. But when it's viewed on the same monitor as a full field of view, you're going to see a larger, because it's using the same pixels, but it's less anatomy, so it's magnified. So reducing the field of view or the active area of your, using less of your active area of your input phosphor, you're going to get a magnification. Okay, since a smaller region of anatomy is displayed on the same size monitor, the resulting image is magnified. Same size monitor, different input on your, different, I guess you say, different X-rays are being hit on the different, a smaller area of the input phosphor. I hope I didn't confuse you on that. So we're just taking, say, 30 centimeter, and we're going to reduce it down to an 18 and then maybe a 10. So we're using less of the input phosphor, and you're seeing less anatomy. Okay, but that action of the X-rays going through and the light photons and the release of electrons, the same thing's going to happen to them. Okay, but there's less of them. There's less light being produced from the X-rays because there's less X-rays hitting the input phosphor because we're using a smaller area of it. We're not using it in full capacity. We're using less of it. So, of course, less X-rays will be involved. Less light will be emitted from the X-rays. Less electrons will be emitted from the light. So that in itself is going to do what to the brightness? It's actually going to reduce the brightness because we got less energy. We got less of them going in, even though they're going through that same process of being minified. but you're actually got less of them to condense down because we're using a smaller area of the input phosphor. Now, since a smaller region of the anatomy is displayed on the same size monitor, the resulting image is magnified, but it's less bright because of what I just said. We're using less of it. We have less interactions with the X-rays, less interactions with light, less electrons. So the image is going to be less bright. It's not going to be as bright. And what the machine does, it actually amps up your MA to maintain that same brightness on the monitor. Now we have a magnified image. It's actually dimmer, but the machine automatically boosts your MA, which is going to cause it to become brighter. So if we're boosting up our MA, and this is through the X-ray tube under the table, what is more MA going to do to our patient exposure? Patient exposure is actually going to go up in the magnification mode. Okay, that's the downside of using the magnification mode. It's a dimmer image, but the machine can compensate for that. But because of the dimmer image and the machine compensating, it's compensating at the sake of patient exposure. Your image resolution goes up really well. It's magnified. You see a lot more detail, better detail, because it's displayed on the same monitor with the same number of pixels, but it's less area to be spread out. So each area on that image has got more pixels because it's less of the anatomy being projected on the monitor. It's the same monitor if you were using the full field of your your input phosphor, or less. So that's what your multi-field tube means, that you can actually use the full diameter of the input phosphor or different steps. I think in page 679, it says that a tri-mode can have like a 23 diameter, an 18, and then a 12. And of course, the smaller of the area of your input phosphor, the larger the image will be, but it's less anatomy being viewed. So it's magnified. So you have a smaller field of view, but it's filling up the same viewing station. It's a little confusing, a little tricky there to understand. So read that in your book. It says on page 679, that first column, it says the magnified mode can be used for better spatial resolution. This is the bottom of the first column. It's right under, above the figure 38-8. It says the number of pixels available in the final output image, the TV monitor, is the same, yet the area of the anatomy being inputted to the image intensifier is smaller. Smaller area of anatomy, same number of pixels. So yes, you're going to have better spatial resolution, but because it produces a dimmer image, the machine boosts the exposure of the actual X-ray tube, so patient exposure is going to go up. Okay, and here it tells you how this happens. In the magnification mode, by moving the focal point, this is your focal point right here. This is where these electrons, because they're being focused into this bottleneck, and I'll tell you one thing, this side here becomes the opposite over here because they're forcing them in a straight line. It's pretty neat. The image actually is flipped when it comes out. But anyway, by increasing the acceleration on these accelerating plates here and the accelerating anode, it says by moving the focal point of the electron beam closer to the input phosphor B, a smaller region of the input phosphor is projected onto the output. So as we put more voltage on these, it pushes them in even tighter, causing your focal point to move closer to the output. You can see where this one's here, this one's way back here in relation to the accelerating anode. So for the magnification mode, it actually what actually happens is you're increasing the acceleration of these accelerating lenses here and your anode. So all of these are getting stronger and it's pushing them in even deeper. So the actual focal point, as the voltage is increased even greater here, it moves closer to the output and further away from the output. Okay? I was going to read that somewhere. I had a pretty good explanation in the book. I hope I explained it well enough. Focal range. Okay, yeah, on page 678 at the very bottom, carrying over to 79, it says, however, it may be necessary to focus in and magnify a selected region of the patient's anatomy. This can be accomplished on most image intensifiers by changing the electric charge on the electrostatic lenses to bring the focal point of the electron beam closer to the input phosphor. In this way, the beam is narrowed towards the input phosphor such that a smaller region from the input phosphor is projected onto the output phosphor. Since a smaller region of the patient's anatomy will be displayed on the same size display monitor, the result is magnification of the image. Okay, everybody got that? Okay, I'm going to go right on over on page 679. I'm going to cross over. It says the magnified image will be, I said this, dimmer. This is due to the smaller field of view being inputted. There is less input light per output pixel. Magnification gain is actually reduced. The loss of light intensity means that the SNR, signal-to-noise ratio, is lessened and noise will become more visible in the image unless the level of light intensity is restored, and that is restored by a system called automatic brightness control. ABC, automatic brightness control. It does it automatically. It brightens it. It controls the brightness automatically. ABC will increase the MA or the tube current, the tube, not the intensifying tube. Okay? But it's actually talking about the tube itself, the X-ray tube. In turn, the increased MA results in more skin dose. So exposure to the patient is increased by the ratio. We wouldn't really know that. You're not going to have to calculate it. But it's an incredible. It says in the next column, it says, you will see that these increases in patient dose will be significant. They can be as high as 3 or 4 times the normal exposure. So from going from a full input to a smaller input to get the magnification mode, your patient exposure is going to be increased by a factor of 3 or 4 times more. So in the magnification mode, you get a weaker image. The ABC corrects it by amping up your MA. Patient exposure goes up. You get better resolution. Remember, because you're getting less information pushed on the same out through the same number of pixels. Same number of pixels are going to be over here connected to the monitor. We haven't talked about the. Remember, we stopped where the actual billions and billions of light is coming out of the output phosphor. That's where we stopped, but they added the monitor here because we'll be covering that later on. Okay, dual mode or tri-mode intensifiers allow different magnification levels to be selected at the push of a button. Those numbers 23, 18, and 12 are actually buttons. You just push them. Sometimes there's little symbols and it's showing you big, like a big M, middle M, and a tiny M. But anyway, those are levels of magnification. Simply pushing the button. Magnification mode can be used to improve spatial resolution or sharpness in the image. And this is a smaller anatomical areas displayed with the same number of pixels available on the monitor. Therefore, there are more pixels per area of anatomy because we have less anatomy, so we got more pixels. The smaller details can be made out. Magnification mode produces a dimmer image. With a smaller input area, magnification gain is lost. Okay, magnification gain is lost. When you're in the magnification mode, that's causing your dimmer image. Magnification mode and patient exposure. To avoid the appearance of noise, from a poor SNR, like we said this on page 679, the ABS, automatic brightness control, increases the MA to compensate for the loss of the minification gain. Patient exposure increases by the ratio of the change in the area of the active input phosphor used. You just want to know there, we would not be calculating this. Definitely want to say this in red. Increases in patient dose can be as high as 3 or 4 times greater than normal exposure if you are using the full input phosphor. As you go to the smaller ones, you're increasing your patient exposure 3 to 4 times higher. We're not going to be doing the calculation here. Okay, I think I'm supposed to stop there. I told Dr. Haynes I would stop at automatic brightness controls, which these are the types or the ways that the system actually, I think I skipped one. Oh, I got 3 and 4 there. Anyway, we're going to stop the PowerPoint here, and I will pick this up probably in the fall, guys. Really, that's what I want you to know is about the brightness gain. So hopefully this helps out. We will cover this again tomorrow at 10 o'clock, along with the components of the image intensifier. It shouldn't be too complicated. Hopefully you'll get time tonight. I apologize for posting this so late. I've had a horrible day on as far as internet connection. I think I finally got it resolved, and hopefully I'm up and running again. But if you guys have any questions whatsoever, please have them ready for me tomorrow, and hopefully we'll have a good productive lecture, and I will see you at 10. Have a good night.